This is Alan Noel Bungling presenting my vibrational analysis for a mass of a cantilever beam. We are given the dimensions and weight of said object in the problem statement, and we are asked to find its log decrement, stiffness, damping coefficient, and damping ratio for theoretical and experimental cases. Here is the equipment utilized to capture the motion. In 3 different multi-views, we have slow motion, horizontal, and regular camera views utilizing VFox with the position, velocity, and acceleration graphs given. Here is our object given with its mass and its dimensions. We're going to treat it as a cantilever beam because it is a rigid structure while the other end extends horizontally into space. Here we have the calculations for theoretical and experimental. Some things to note is that we assume that our xi value is small 0.01 for a log decrement calculation, and we're going to assume that the effective mass is going to be the same for both since we did take that measurement for the givens and assumes. And of course, to make those inferences and calculations more clear, we have the table of those calculations. Like we said, there's a little deviation in the damping coefficient because we assume the xi value, but regardless, we're able to come up with equations of motion when it comes to theoretical and experimental cases. Here we have the VFox position, velocity, acceleration times, where I took the peak-to-peak amplitude for my calculations in the previous 2 slides. To improve this experiment, we could add a second degree of freedom because the original experiment is just the cantilever beam moving in a vertical direction. We've learned that the damping coefficient determines how quickly oscillation returns to equilibrium and whether it oscillates. The log decrement measures how quickly the amplitude of a damped vibration decreases over time. And some takeaways could be like some sensor sensitivities that could be improved with a different background.